So we had a little bit left to do in 15.2. Today we're going to do 15.3 and some of 15.4. Seniors, this will be the last sections that are last topics that you'll be responsible for on your exam, or what we go through today.
Wow, I need to do.
I know, right? All right, so continuing in 15.2, we had a couple of ideas still left. So in 15.2, we'd been talking about like exponential models, so like some real life situations in which we can use our exponential function. So we talked about like exponential population growth. Another application is half-life. If you've taken a chemistry or a geology class or something, you probably talked about. Hi there, sir.
Yes.
Thank you, dude. You've probably talked about radioactive decay at some point. The idea is you have a radioactive isotope. Over time, it emits radiation. That radiation has mass to it. Over time, that element then loses its mass, loses protons or neutrons or whatever, and decays into a new element. That process is called radioactive decay. Typically, we measure how radioactive a substance is by the time it takes to lose half of its mass due to radiation. We call that length of time the half-life. For us, we'll still be using that same population model. The only difference here is that when you see half-life, you should immediately recognize that the R here is negative 50. So negative 50% is half-life. It's negative because you're losing stuff, it's decaying. It's an exponential decay problem, and 50 because it's a half. You're losing half. All right. It says, suppose the half-life of a certain radioactive substance is 35 days, and you have 10 grams of the substance initially. Find the time it would take for there to be 1 gram remaining. So if we go back and we use our population model for exponentials, we have something that looks like this. So the P naught is the initial amount. So that's 10. Because it's a half-life, we know R is negative 50. And now, how are we going to pack this 35 days? What is that going to mean? Right, well, it means that when T is 35, I want to divide that mass by 2, right? So that means that I want to have T over 35. So when T is 35, we just have 1/2 to the first. That's what we want to have happen. So I can do a little bit of simplification here. Thank you. So 1 plus negative 50 over 100 is just 0.5. Now it asks, so that's my step 1, right? Just like set up my model. Step 2 is going to be then to solve the model when P of T is equal to 1. So again, when we do this, we're going to do this graphically. So I'm going to have the right-hand side in y1, and then the left-hand side in y2. I'm going to go ahead and set myself a window. Remember, the x-coordinate is our time. So if I think about this, after 35 days, I'd have 5 grams remaining. After 70 days, 2.5. After 105, 1.25. And somewhere after 105 and before 140, I'll dip under 1, right? So I'm going to just go, X max will be 140 because I know before 140 that'll happen. The Y minimum, this is decay, so it's decreasing. The least amount of mass you can ever have is 0. The Y maximum is just the starting amount because that'll always be the biggest you could ever have. And that'll do enough for me to get a good window. So I press graph. Here's my decay function. There's my line for y equals 1. There's my intersection, second trace, intersect command, enter, enter, enter. And T is about 116 days. Everybody feel about okay there? When we talked about logistic models last class, we talked about how they can also be effective population models because of the 2 asymptotes that they have. So let's look at an equation where we use a logistic model for population rather than a strictly exponential model. In the case where we do this, you'd always be provided the exponential model in the problem. It'll just tell you that this is the logistic model in the problem. It'll just tell you here's the model. So you'd never be expected to write your own logistic model. Part A says, how many bunnies do we have initially? What time does initially mean? What does the word initial mean for time? It's 0. So we're just going to be calculating B of 0. So when I do that, I get 8 cute little bunnies. Part B says, what is the maximum sustainable population of your bunnies? So remember, for all logistic functions like B of t, we have 2 horizontal asymptotes. One at y equals 0 and the other at y equals c, where that guy is c. So this 800 is my maximum sustainable population. Can't have more than 800 cute little bunnies hopping around my farm. And then part C says, how long will it take to have 500 bunnies? So all I really need to do is solve for B of t equal 500. Again, to do that, I'm going to be using my calculator. So alpha y equals first fraction option. So I'm going to type this B of t in exactly like it looked on my calculator. And then the other side is 500. I'm going to reset my window. T is years. The only thing I know about bunnies is they reproduce really quickly. So I'm just going to go 0 to 10. I don't really know, but that's going to be my guess. The y's I do know. I know that the minimum y is 0 and the maximum y is 800. So that seems pretty easy. And let's go ahead and hit graph and see what I get. So here's my population curve. Okay. Well, I didn't quite make it. Guess we'll have to make that a little bigger. So like maybe we'll make that 20 years. Try it again because you saw they didn't intersect. There we go. That's a nice S-looking curve. There's my intersection. Second trace, intersect command, enter, enter, enter. 10.2 years. So after 10.2 years, those 8 bunnies have turned into 500 bunnies. Get it, bunnies. They're getting busy. That was supposed to be funny. Nobody laughed. Thanks, guys. I'm trying to be somewhat entertaining, and I just seem like I'm annoying. Oh, man. That concludes 15.2. In 15.3, we're going to start talking about logarithmic functions as opposed to logistic functions. So when we say a logarithmic function, we define that using the definition based on the exponential. So we say that the exponential equation b to the y equals x is equivalent to the logarithmic equation log base b of x is equal to y. In essence, a logarithm is just like log of, c or whatever. It's just a number. That number represents an exponent to solve a exponential equation. So like what power of 2 gives me 3 is log base 2 of 3. Everybody's okay with that idea? It's just like the name we give something. So let's do a little bit of practice here. All right. So what I would do is I'm going to write like equals, well, let's do it down here. So what I'm going to do first is I'm going to say this is equal to y. And then I'm going to use my definition here from above. So this says that I can rewrite this as b to the y is equal to x. So what power of 4 is equal to 16? Oh, come on, guys. It's not a hard question, is it? What power of 4 is 16?
2.
2. Yeah, that's all. So continuing on, kind of do the same way. So I do b to the y is equal to x. So what power of y, or what power of 5 is the square root of 5? Does anybody remember what exponent is equivalent to a square root? It's 1/2. Remember that? Right? That's our property of exponents. So what does y got to be then? Oh, come on. It's sitting right there. 1/2. Thank you, Avery. Reach out and grab it. AJ wanted that one. There's some on the power strip up here. You can plug it in for a bit. So again, I take b to the y is equal to x. Now, the way this is currently written, it's not super obvious how to figure out what the y is. So what I'm going to do is I'm going to work on that 1 over 27. 27 I recognize as 3 to the third, right? Everybody's okay there? And I recognize that I can use this property of exponents. That I know that a reciprocal is the same thing as a negative exponent. So what does that tell me y is? Dude, it's negative 3. So the next one, again, I do b to the y is equal to x. Well, what power of 12 is equal to 1? Oh, nobody? 0 is the right answer. Remember, any non-zero number to the 0 is 1. Just as an aside, what's 0 to the 0? Undefined is correct. Good memory. So in our last one, we can say b to the y is equal to x. So what does y have to be here? Come on, guys. It's just going to be 1, right? 8 to the y is equal to 8. So y has to be 1, right? It's kind of inspectionable. So a couple of takeaways here from what we just did. Some properties of logarithms that are always true. Here, what we can, oh, come on now. So I can say log of 1 is 0. That's what we saw in D. Yes, sure. We can say log base b of b is 1. That's what we did in E. But why are these two true? That doesn't seem as obvious. Well, remember that log base b of x is equal to y, and that's equivalent to saying b to the y is equal to x, right? So what if I take this y, let's take this x and plug it in over here. What would I get? I'd have log base b of b to the y is equal to y. Aha! That's exactly what we have up there, right? What is that really saying? It's saying that log base b will cancel the exponent base b, and we just left with y equals y, right? Similarly, if I take this y and I plug it in, I'd have b to the log base b of x equals x. Well, that's what we have here. What that would be implying is that exponent base b cancels log base b, these two ideas are the most important concepts to walk away from in this chapter. If you can keep that straight, that that's how we cancel out an exponential or how we cancel out a logarithm, everything moving forward will be considerably easier. That is the core concept that we're going to see in chapter 15, is this inverse relationship between exponentials and logarithms. Okay. Now, you notice when we write these logarithms, they all have like this base b in them, right? We have to write some number in the subscript there for the logarithm. That number, just like an exponential function, has to be greater than 0 and can't equal 1. But there are two values for b that are special, that we get used a lot, that we're going to create a special shorthand notation for. The first value for b is when b is 10. We call that type of logarithm, whose base is 10, the common logarithm. And we just write it as log with no subscript at all. Just like when we write a square root, we don't write the index 2 in the check mark like we would for a cube root. We just don't recognize it when there's nothing there, it's 2. The same idea with the common log. When we write log with nothing in the subscript, we know that that something is 10. Everybody's okay with that? So log is log base 10. The other special logarithm is log base e. That one is referred to as the natural log. And when we write log base e, we just write the letters ln. So when you see the letters ln, that is log base e. So a couple of examples. We could do this exactly like we did the previous problems, but I'm going to try to do this in a different way to emphasize this idea of like logarithms canceling exponent bases or exponent bases canceling logarithms. So the first problem is log of 1,000. Well, when I look at that, I recognize that when I write log with no base, that means the base is 10. So if I have log of 1,000, what I want to do is find a way to rewrite 1,000 as a base 10 number. So 10 to what power is 1,000? Well, I know 10 times 10 is 100. And then 100 times 10 is 1,000. So I multiplied 3 tens together, that's 10 to the third. And then log base 10 cancels with exponent base 10, and we're left with 3. This is the way that I prefer to think about simplifying a logarithm. I think they are easier. I think it's an easier way to thinking about it. So again, I have log of the 5th root of 10. Well, again, because it's just written log there, I know that the base is 10. So I want to start by rewriting the 5th root of 10 as 10 to some power. What power is the same as a 5th root? Oh, come on, guys. That's the rule we're using. What power then? Anybody? Thank you. Goodness gracious. It's even a senior who's like only nominally paying attention here. All you juniors should be embarrassed. Plenty embarrassed. So log base 10 cancels with exponent base 10. We're left with 1/5. Again, it's just written regular old log. So I know that's log base 10. And then 0.01. What fraction is 0.01? It's the same as 1%. What fraction is 1%? 1 over 100, right? If you couldn't do that in your head, you could have typed in 0.01 to your calculator and done the fraction command. It would have spit out 1 over 100 for you. And I recognize 1 over 100 as, well, 100 is 10 squared. And when I have a reciprocal like that, oops, I know it's the same thing as a negative exponent. And then I'm left with just the negative 2. In D, I have e to the ln 5. I recognize ln as log base e. And I know that exponent base e cancels with log base e. Just have 5. Woo! It's amazing, Mr. Kulak. I know. Ooh, tricky. 2 equals, I have regular log written there, so I know that's log base 10. Now, what do I have to do to both sides to get rid of this log base 10? I need to use exponent base 10 to both sides. Do it down here. So I'm going to really exaggerate the size of that 10. Now, I know that looks pretty silly with how big that 10 is, but I really want to emphasize that you're not multiplying both sides by 10. The left-hand side becomes 10 to the second, and the right-hand side becomes 10 to the log 10 of x. Again, exponent base 10 cancels the log base 10, so we're left with 10 squared is x, or x is 100. Similarly speaking, we have natural log of y is equal to 5. Remember that natural log is log base e. So what do we need to do to both sides to cancel log base e? Exponent base e. It's like I'm having a conversation with myself today. And if you wanted to, you could type in e to the 5th to your calculator, but nobody wants to do that. It's just some big kooky decimal, right? I've had enough of big kooky decimals for the day. Now, remember when I told you that we could type in log base 2 of 3 into our calculator? We use the math button. We scroll almost to the bottom and we get that log base command. So you can do log base 2 of 3. But if I just want to do log of 10, or I'm sorry, log of 3, well, right here above the on button is just the common log. Or if I wanted the natural log of 3, the ln button is right underneath the common log button. Notice that if I did, log base 10 of 3, I should get that same 4.77 that I got when I did just log of 3, and I do, right? So just the buttons on the calculator main screen are just time savers, right? But you could type in log base 10 of 3, or you could just type log of 3. Either is okay. Cool beans. So notice when we did this, when I showed you this right here? Does anybody recognize this? This is something that we did way back in first semester. What are we saying here? It's like the first chapter that we did in first semester. These two statements are equivalent to saying that like f of g of x is equal to g of f of x that are both equal to x. What is that the statement for? It's that those two functions are inverses of one another. So, since they are inverses of one another, that means that every property for exponents has a corresponding property for logarithms, and vice versa. So for example, for exponents, we know that like a to the n times a to the m is a to the n plus m, right? That multiplication outside of the exponential turns into addition inside the exponential. The opposite is true for logarithms, where multiplication inside the logarithm turns into addition outside the logarithm. But you see how that's an equivalent property? I know for exponentials, if I have a to the n divided by a to the m, that's the same thing as a to the n minus m. So division division between the two exponentials turns into subtraction inside the exponentials. The opposite is true. Division inside turns into subtraction outside, and we can kind of continue doing this. This property is like, this power property is like the product or the power of a power property for exponentials, and this kind of continues on. Now, the change of base formula here is an interesting piece. This was super important when I was a student your age. You guys don't really even care about this anymore. The reason is, when I was a student, if I wanted to do log base 2 of 3, I had to rewrite that as the natural log of 3 over the natural log of 2. Because I didn't have a calculator that could do a logarithm. Any logarithm at all didn't have a calculator that could do it. So what I had to do is I had to flip to the back of my textbook. I'd have to look up the values out of a big table, write the values down, and then type like 0.07 divided by 0.008 or whatever into my calculator and press enter. Which stinks. How are you going to do log base 2 of 3? Well, Mr. Kulik, I'm just going to use the log base button on my calculator, right? Like I'm not. So the change of base formula is not really super meaningful to you because of the power of your technology you're wielding versus the technology I wielded as a, high school student. Do you feel bad for me yet? With these properties of logarithms, typically we ask you to do 2 problems. So those 2 problems are expanding. So with an expansion problem, you take one logarithm and you turn it into the sum or difference of many logarithms. With expanding, we do quotient property, and then product property, and then power property last, unless there's some like parentheses kind of implying that one of these things has to happen before the other. The other type of problem is called condensing, where we take the sum and difference of many logs, and ideally we combine them all together into a single log. Condensing, we go the opposite direction. We go power, product, and then quotient. Typically. Everybody ready to rock and roll? Let's do some examples of doing this. Do you remember doing this last year in your Algebra 2 class? You should, because you should have spent a good bit of time doing this. This is a core logarithm skill for Algebra 2 students. All right. So it says assume all variables are positive, whatever, I don't care about that. Expand the following logarithmic expressions using the property of logarithms as much as possible. So it says expand. Yep. Yep. He's the little engine that could. All right. So when we're expanding, the first thing we look for is a quotient property. So I look inside my logarithm. Is there anything being divided? No. No quotient property to do. Okay, well, I'll move on to my product property. I look inside my logarithms. Is there anything being multiplied? Well, yes. Right? If I look at 4x, I know that's 4 times x. So there is one product property going on. That allows me to write this as log base 3 of 4 plus log base 3 of x. Any questions so far? The last thing I look for when I'm expanding is then for a power property. So if I look at log base 3 of 4, and I look at log base 3 of x, do we see, if we look inside the logarithms, do you see any exponents there? At first glance, you say no, right? I see 4 to the first and x to the first, whatever, there's no powers there, because 1 doesn't really matter. But be careful here. Your math teacher is a tricky jerk. 4, we could also think of as 2 squared. That now is a power property. So the power property, the exponent comes to the front, and the base stays inside the logarithm. That will be our final answer, our best answer. Again, new problem. I start by looking inside the logarithm. Do we see any quotient properties going on? No, Mr. Kulik, there's no division. Okay. Do we see any product properties going on? Well, yes, Mr. Kulik. How many product properties? Should be 2, because I see multiplication in between the 3 and the a, and in between the a and the b to the 5th. So when I apply those 2 product properties, I can rewrite that as log of 3 plus log of a plus log of b. Now if I look inside each of these logarithms, I'm looking for a power property. 3, no power property there. A, no power property there. B to the 5th, that's a power property. So I'm just going to recopy the first 2. And then log of b to the 5th becomes 5 log of b. Again, the exponent moves to the front. The base stays inside the logarithm. Last example, we have natural log of 2x over the square root of x cubed minus 5. First thing I look for is a quotient property, and aha, I finally see one. Definitely division going on there. So when I apply the quotient property, I'm going to have natural log of the numerator minus natural log of the denominator. Now I'm going to look for product properties. Again, I look inside each of the logarithms. I see a product property with the 2x, but there's no product property with the square root. So applying the product property, it gives me log of 2 plus log of x. Last thing I look for now inside each of my logarithms is a power property. No power property with the 2. No power property with the x. But there is a power property with the square root of x cubed minus 5. What is the power going on with the square root of x cubed minus 5? Very important question. What is the power going on? Who thinks it's 3? 3 is wrong. Well, what is the power then, Mr. Kulik? It's not 1. The power is coming from the square root. What exponent is the same as a square root? Not 2. 1/2. Now, why? Yes. Now, why aren't I able to take the 3 out from the x cubed? Very important question. Mr. Kulik's telling me I'm done, but I still see a power inside my logarithm. Why is that power still left there? For the power property to be used, that power would need to go around the entire thing. Right now, the power is only attached to the x. So if it was x minus 5 cubed, then I could do a power property on that. But x cubed minus 5, no power property. Do you guys see the difference? I'm going to erase that piece now. Let's look at some condensing examples now. So when we're condensing, we're going the opposite order. So the first thing we're doing is looking for power properties. But because we're going the opposite direction as well, instead of looking for an exponent inside the logarithm, what I'm doing is I'm looking for a coefficient in front of the logarithm. I'm then going to look for a product property. Again, for the product property, because we're going in reverse order, instead of looking for multiplication inside the logarithm, I'm looking for addition between 2 logarithms. So I see it there. And then my last one, I'm looking for a quotient property, so I'm looking for subtraction between two logarithms. But I can't actually do a quotient property here on this problem. Why not? Look at what I have. Why can't I do a quotient property here? What is wrong with what I've written? Whoa. It's a big bird that just flew by. What's wrong with these two logarithms? Why can't I use a quotient property on them? There's subtraction between them, Mr. Kulik. What's wrong with it? Look at the bases on the logarithms. In order to use either the product or quotient property, the bases of the logarithm must be the same. They were here when I did the product property. They are no longer the same, though. Notice in the beginning, one of them was log base 5, so that's as good as I can do. So I'm done. Okay. First things first. Power properties. I see 1, 2, 3 power properties. So let's crank those out. Yes. Yes. Now, look at what I've written. Mr. Kulik has intentionally made a mistake. So look at this step. I've intentionally made a mistake. Can anybody identify what the mistake is? I did this because, in my experience, at least half of us would make the same mistake, if not the majority of us, without me pointing this common mistake out to you. But I've made a mistake. What I've currently written is incorrect. What is the problem? I love doing this because it's, I think, sticks in your head after you've been pointed it out this way. Like, I did something you would do, but it's wrong. Can you find what I did that was wrong? Nobody? Oh dear. I'll give you a hint. It's in the middle logarithm. It's in this piece that the mistake is happening. Can anybody see it yet? This is the mistake. That exponent of 3 needs to apply to both the a and the b. So you could write this as like a cubed, b cubed, if you wanted, or with a parenthesis around the ab. But you can't write ab to the third, because that means a to the first, b to the third. That's not what we mean, though. See how easy of a mistake that would be to make? That's why I'm pointing it out to you. Next thing we're going to do is we're going to look for a product property. I see a plus sign, so there's a product property, right? Here's the catch, though. The product property is not happening between the two logarithms you think it is. If you go back and you look at the formula for our product property, both of our logarithms have to have coefficient of 1, right? If I look down here, this logarithm has a coefficient of -1 because of the subtraction symbol there. So if I'm doing a product property, it's actually happening between these two guys. Oh, Mr. Kulik. Why is it okay to do that? Yep. Well, remember, we can add things in any order we want, right? Addition is commutative. So just because they're not next to each other doesn't mean I can't add them together. All the positive stuff needs to go together in the same logarithm. It's got a subtraction sign in it. Oh, no, 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 no. That's now going to be my quotient property. And hey, hold on a second, Mr. Kulik. What do you notice that can happen here inside this logarithm? Look at that fraction. What can you do to it? It starts with an R. Ugh! Reduce! Yes, there you go. So that would end up just being A over B. Let's get that. All right. 15.4. Yes. Yes. In 15.4, we're going to talk about solving exponential and logarithmic equations. To do this, we're not going to be using any new ideas. We're just going to be recycling the same ideas we've used before. So we're just going to be using like our normal reverse order of operation solving algorithm, along with this idea that exponents cancel logarithms and logarithms cancel exponents. So remember, we have the order of operations, but since we're solving, we're kind of working backwards, right? First thing I'd want to do is undo any addition and subtraction. I do see some subtraction going on, but it's locked in the exponent, so I can't get to that until I've knocked that exponent, knocked that x minus 1 out of the exponent, right? So we won't do that. Next thing I look for is multiplication and division. Well, I see multiplication going on here, so I'll divide both sides by 14. 126 divided by 14 is 9. Now, how do I cancel out this exponent base of 1/3? What do I need to do to both sides of this equation to cancel out that exponent base of 1/3? I need to use a logarithm. Any logarithm will work, but it could get messy. I'm going to choose a logarithm of a specific base in order to keep it simple. Which base do I want to choose my logarithm to have? I want it to have the same base as my exponential. Log base 1/3 cancels exponent base 1/3. And then I just add 1 to both sides. And then it's calculator time. So math, log base 1/3 of 9 plus 1 is -1. And I'm done. What do you guys think? That first step, or that step of using a logarithm to cancel the exponential, is critical. Gotta see it. All right. Next example, same kind of problem. I don't see any addition or subtraction right away. So I'll start just by dividing both sides by 12. When I do that, 12 divided by 27 reduces. That is going to give me 9/4. Now, what do I do to both sides to cancel the exponent base of 3/2? Please, for love of Pete, somebody tell me. What do I need to both sides to cancel out the exponent base of 3 over 2? Come on. Come on. Let me give you a hint. Log base. What should the base of logarithm be? What should it be? Come on. Come on.
5.
No! The same as the exponents. So 3 over 2. Always the same as the exponents. Disappointed. Multiply both sides by 5. And then it's calculator time. When I type that all into my calculator, I get 10. Or you could do it in your head if you're a math teacher. All right. Here is the trickiest situation. Let me show you this one. Why is this trickier than the previous examples? What's going on here that's different and new and maybe makes it unclear as to what to do to deal with this? Where's the variable at? It's in 2 different exponents. Oh no! Well, we'll show you how to deal with that in a moment. First thing, though, that I'd want to do, I'm just going to multiply both sides by 4 and get rid of that stinky fraction. Everybody's good there? Can I add 3 to the x and 3 to the negative x? Can I add those two things together? No! To add things together, they must be identical. Are they identical? No, one of them, the exponents are different, right? Okay. So what am I going to do here? What I want to do is I want to get the exponents all to be positive. I don't like that negative x up there. What can I multiply 3 to the negative x by so that its exponent isn't negative anymore? Well, 3 to the negative x times negative 1 is just negative 1 times 3 to the negative x, right? What I want to do is I want to multiply both sides by 3 to the x. So 3 to the x times 3 to the x is like 3 to the x squared. 3 to the x times 3 to the negative x, I add the exponents. So that's going to be 3 to the x plus negative x. And the last one is 8 times 3 to the x. What is x plus negative x? 0. What's 3 to the 0? 1. Look at what you have here. Look carefully. Look very carefully. What do you see? What type of problem do we have now? Nobody sees it? Let me help you. Let's take those 3 to the x's and just replace them with the variable y. What kind of a problem do we have now? Come on. What do you call that thing? What type of an equation is it? Starts with a Q.
Quadratic.
It's quadratic. How do you solve a quadratic equation? Well, it's got to be equal to 0. And then I'll either try to factor or use the quadratic formula. Well, there's not two things that multiply to give me 1 and add to give me negative 8. So quadratic formula it is. So negative b plus or minus b squared minus 4ac all over 2 times a. So that comes out to be 8 plus or minus, that's the 64 minus 4 is 60 over 2. But wait. We didn't want to solve for y. We want to solve for x. Right? So we got to put that back. So instead of y equals 8 plus or minus square root 60 over 2, we're going to have 3 to the x equals 8 plus or minus square root 60 over 2. How do I get rid of that exponent base of 3 to get the x by itself? What do I have to do to both sides? Come on. What's going to cancel out that exponent base of 3? This guy right here. We got to get him out of there. What do we do? No! Division's not going to help.
Square root.
No! Square roots. Starts with an L. Log. What base of logarithm do I want to use on both sides? 3. Why 3? It matches the exponent base. Exactly. So we'd say 8x equals log base 3 of 8 plus square root of 60 over 2, or log base 3 of 8 minus square root of 60 over 2. To get those values, we go to our calculator. So log base 3 of, and I'll use the fraction command there, 8 plus square root 60 over 2. So 1.87, and then just change that to a minus. Negative 1.8, well, negative 1.88. That's the worst case scenario, is when you have a exponential equation nested inside of a quadratic. That is your worst case scenario. Okay. Let's move on to logarithmic equations. Same idea. So first step, I have 3 log of x squared equals 6. First step, what do I need to do? Trying to get x by itself. What do I need to do first? This is like a pre-algebra question. Your little brother in middle school would be able to answer this. Where is the hesitation coming from? First step. To do that, what do I need to do, though? Divide by 3, homie. Yeah, that's it. Well, don't be scared, right? Take a risk. You know, like, you're going to be gone in like 6 days or something. No one will even remember. If you make a fool of yourself, you won't even be here to face these people anymore. All right. How do I get rid of that log in front of the x squared? What do I need to do to get rid of that log in front of the x squared? I'll give you a hint. The base of this logarithm is 10, because I know that when I don't write anything, it's base 10. What is going to get rid of that log base 10? It is, you guys, exponent base 10. I'm scared for what this is going to look like when you have to do this on your own. Log base 10 cancels exponent base 10. So I have x squared is equal to 10 squared. So x equals plus or minus 10. When I square root both sides, right? Everybody okay? Guess what, though? We're not done. All logarithmic equations must be checked for extraneous solutions. Fortunately, the check is really easy. All I need to do is take my value for x, plug it back into my beginning equation to see if I get a negative number inside my logarithm. The good news is that negative 10 squared and positive 10 squared are both 100, so they both work. Both these answers are okay. No extraneous. Got one more example for today, and then we're going to take a stopper. Oh no, Mr. Kulik. What do you notice that's going on this one? What's different about this problem than the previous one? I have variables in 3 different logarithms. Oh no! What should be my first step? That's my end goal, homie. We're going to be a while before we can do that. That's the overall goal. First step on the way to doing that, though, is I'm going to get all the logs on one side. So to do that, I'm just going to subtract log of x to the other side. Oops, I'm at 2 log of x. Excuse me. Hey. Look at what we got here. Ooh, do I want to do that way? Maybe I want to leave it. Let's leave it. I think that'll be okay. Let's not move it over. That's what actually I think will make life easier. All right, what am I going to do? What am I going to do? I'm condensing the logarithms. On the left side, I see a product property. On the right side, I see a power property. You thought you were done with that stuff. It's like, okay, I can see how to do these problems. It's pretty dumb, like it's just a problem. Oh no, they pop up in solving. So far, so good. How do I get rid of these natural logs, right? If natural log of something equals natural log of something, what cancels out a natural log? Exponent base, which base? No! No! What is the base for ln? We just talked about it not that long ago. E! Thank you! Somebody was listening. Awesome. So we do exponent base e to both sides. So I end up with 3x minus 2 times x minus 1 equals x squared. What type of problem have I been left with now? It's quadratic, my man. Let's FOIL this thing out. So 3x squared minus 5x plus 2. Subtract x squared from both sides so that it's equal to 0. We could try to factor that. I think it'll factor, but its leading coefficient isn't 1, so I don't like that. I'm just going to use the quadratic formula on it. Negative 5 squared is 25. Minus 16 is 9. Square root of 9 is 3. 5 plus 3 is 8. Divided by 4 is 2. 5 minus 3 is 2. Divided by 4 is 1/2. But we're not done. What do we still have to do? Gotta check. So if I go back to the top, 3 times 2 minus 2, that's positive. 2 minus 1, that's positive. 2, that's positive. That's an answer. Got to check my next one. 3 times 1/2 minus 2 is negative. Stopping. Crossing it out. That's extraneous. As soon as I get any negative by plugging in my answer to the original problem, I stop. I am done. 1 negative is enough, or 0. 0 is bad too. Everybody good? Here we're stopping. You can now do, last time I signed up through 36, you can now do up through 30. 130. Next class, you can expect your homework quiz. Really, if you've done the 15.1 and 15.2, you should be good. That's the 1 through 36.
We're not going to be here. We're not going to be here.
Then it'll be the next class.
Why wouldn't you be here?
All the juniors are college.
Yeah, that's
Oh,
swell.
is that what your dad was talking about?
On the announcements.
Did he just tell you that stuff at home? Oh,
Yeah, Colin doesn't listen then either, though. And here I'm going to stop because this is, well, we're almost done, and 2, that was a lot for today.